Hello everyone. In this video, we will talk about the hypergeometric distribution. Recall the binomial probability distribution. We use this distribution to model the number x of favorable or unfavorable outcomes. Ideally, it is applicable when sampling is with replacement for the binomial distribution. That is, each item drawn from the population is observed and then returned to the population before the next item is drawn. The binomial distribution is only an approximate probability model for sampling without replacement. So when we sample with replacement, we will use the hypergeometric distribution. The hypergeometric distribution gives the exact probability model for the number of successes in the sample. However, the binomial distribution is still appropriate if the population size is large and the sample size is small. Recall the rule of thumb. If the sample size over the population size is less than or equal to 0.05, we can treat the experiment as a binomial experiment. In this video, we will focus on sampling without replacement. The number of successes, the random variable x in a random sample of n items, will follow a hypergeometric probability distribution. Let's take a look at the characteristics that define a hypergeometric random variable. The experiment consists of randomly drawing n elements without replacement from a set of capital N elements. So we have the population size, the capital N, and we draw a sample size of n, the small n. In the population, there are m successes and n minus m failures. So m is the number of successes in the population. The hypergeometric random variable x is the number of success in the sample of n elements. Let x denote the number of successes in the sample. What is the probability that there are x successes in a sample of size n? The sample space, the number of ways in selecting n items out of the capital N items. The number of ways is the big N, C, small n. And then the number of ways in selecting x successes. There are m successes in the population, and we want to get x in the sample. So the number of ways is mcx. And then the remaining items in the sample corresponds to the failure. There are altogether n minus x in the sample. So the number of ways of selecting n minus x failure corresponds to the expression n minus m, and then c n minus x. Out of the n minus m failures in the population, we have small n minus x failures in the sample. So the probability of getting x successes in a sample of size n, p of x equals to small x, equals mcx times n minus m cn minus x over the big N c small n. And this is the PMF of the hypergeometric distribution. The notation, we use H denote hypergeometric. And then there are three parameters. The first one, small n, is the sample size. Big M is the number of successes in the population, and big N is the population size. This is the PMF of the hypergeometric distribution. And the support for X. What are the possible values of X? X is an integer satisfying these inequalities. X is greater than or equals to the maximum of 0 and the expression small n minus the expression big N minus big M. And X is less than or equals to the minimum of the sample size and the big M. M is the number of successes in the population. This expression can be directly derived from the numerator of the PMF. We have the expression MCX, so X should be less than or equals to M. And then another factor, big N minus big M, C small n minus X, and N minus X should be less than or equals to N minus M. So we have X should be greater than or equals to small n minus the factor big N minus big M. Let's take a look at each inequality separately. Under what condition? We have the condition that X is greater than or equals to N minus M. This is the case when the sample size is greater than the number of failures in the population. So in this case, the number of successes in the sample will be greater than 0. Let's take a look at a numerical demonstration. Suppose the population size is 100, and the number of success in the population is 85. Therefore, the number of failures in the population is 100 minus 85, which is 15. And suppose the sample size is 20. There are only 15 failures in the population. So in any sample, the number of successes should be at least 5. So in this case, X will not start from 0. It starts from 5, which is the sample size 20, and then minus the total number of failure in the population 15, 20 minus 15. And other inequalities. Under what condition that X is less than or equals to M? Small n is the sample size, so X should less than or equals to N. How about the condition that X is less than or equals to M? When we have the case that the sample size is greater than the number of successes in the population. For example, the population size is 100. The number of success is 18 in the population. And therefore, the number of failures in the population is 100 minus 18, which is 82. And suppose the sample size is 25. The total number of success in the population is 18, and we have a sample size of 25. So the number of successes in the sample X takes on value 0, 1, and up to a maximum of 18, which is the number of success in the population. All right, then we can do the mean and the variance of the hypergeometric distribution. Let's get back to the binomial distribution. The mean is n times p, and the variance is n times p times 1 minus p. For the hypergeometric distribution, the mean is n times big M over big N. Compare the expression for the hypergeometric and the binomial. In fact, for the hypergeometric distribution, the expression M over N is the probability of success, which is P in the binomial distribution. And then the variance for the hypergeometric distribution, which is N times M over N times 1 minus M over N. This expression is very similar to the variance of the binomial distribution, where M over N is the probability of success, the P for the binomial distribution. So we have N times M over N, which is P, and 1 minus M over N, which is the factor 1 minus P in the binomial distribution. And then there is an additional term for the hypergeometric distribution regarding the variance. Big N minus small n, and then over big N minus 1. This is the finite population correction factor. If we rewrite this expression as 1 minus small n over big N, and then over 1 minus 1 over the population size, this expression is very close to 1 when the sample size is relatively small than the population size. And because this expression, the finite population correction factor, is less than 1, so the variance of the hypergeometric distribution is less than the variance of the binomial distribution. And this is the summary regarding the hypergeometric probability distribution. We have the notation H with 3 parameters: the sample size, the number of success in the population, and then the population size. We have the PMF and the corresponding possible value for X, the mean, and the variance formula. Let's take a look at an example. Of the 20 lecturers in the mathematics department, 12 have been with the department 5 or more years. If 9 lecturers are chosen randomly, find the probability that exactly 4 will have 5 or more years seniority. Let X be the number of lecturers with 5 or more years seniority. This is a hypergeometric distribution with n equals 9. This is the sample size. We choose 9 lecturers. And then the success. The event success corresponds to the lecturer with 5 or more years seniority. Here M equals 12. The number of success in the population. And then the population size 20. The sample size 9 is not relatively small than the population size. Small n over big N is greater than 0.05. So the hypergeometric distribution is more appropriate, and it gives the exact probabilities. So we have X follows the hypergeometric distribution with parameter 9, 12, and 20. We want to get the probability that X equals 4. Exactly 4 will have 5 or more years seniority. Plug the numbers in to the PMF. So we have M is 12, X is 4, and then the population size 20, and the sample size is 9. So we get the expression 12C4 times 8C5 divided by 20C9. Upon calculation, we get the probability 0.165. Let's use the Excel function to do the computation. The function for hypergeometric distribution is hypgeom.dist. hypgeom.dist. It takes 5 parameters. The first one is X, and then the sample size N, the big M, and the big N. And then the last parameter is cumulative, the logical value, 0 or 1, or true or false. Cumulative is equals to true if you want to get the cumulative probability. Otherwise, you set it to false. Redo the problem with the Excel function. So we have sample size is 9, big M is 12, and the population size is 20. We want to get the probability of X exactly equals 4. So this is the Excel function, hypgeo.dist, and then the parameter X equals 4, sample size is 9, big M is 12, population size is 20, and then the logical value false. We get the same answer as we calculated in the previous slide, 0.165. Let's move on to another scenario. This time, we want to find the probability that more than 6 will have 5 or more years seniority. Using the Excel function, plug in the parameters. We have the same distribution, same parameters for the sample size, big M, and big N. What is X, as well as the cumulative value? We want to find the probability of X greater than 6. this equals to 1 minus the probability of x less than or equal 6. We want the cumulative probability at x equals 6. Therefore, the Excel expression 1 minus the hypergeometric distribution function with x equals 6, and then the parameters 9, 12, and 20. And then this time, the cumulative parameters is true. Then we get the probability 0.1569. How about the mean and the standard deviation? Directly plug in with the formulas. The mean equals the sample size times big M over big N. And then we have the variance formula. Plug in the values, and we get the mean is 5.4. 9 times 12 over 20. And then the variance, we get 1.2505. Taking the square root to get the standard deviation, we get 1.1183. And this completes the example. That's it for today's video. Thank you for watching. In the next video, we will talk about negative binomial distribution.